What happens when AI learns to see anatomy instead of pixels, detect anomalies in shifting time series graphs, and uncover the hidden bias that depth imposes on neural networks? In today's episode, we explore three striking papers that push machine learning in very different directions: ultrasound models that distill anatomy-aware representations, contrastive methods that catch anomalies in dynamic multivariate data, and theory that reveals how deep models secretly prefer low-rank solutions. From clinical imaging to industrial monitoring to the mathematics of learning itself, this episode connects practical breakthroughs with fundamental questions about how AI really learns. Let's explore the first paper: Anatomy-Anchored Self-Supervision Distilling Vision Foundation Models for Invariant Ultrasound Representation. Anatomy-Anchored Self-Supervision, or ANA-US, reframes ultrasound pre-training around clinically meaningful anatomical structures instead of whole frames or generic image regions. The key novelty is LP-SAM, a two-stage adaptation of Segment Anything model using lightweight adapters and a learnable latent prompt engine with cross-perception attention, which turns public image mask pairs from DDTI, TG, 3K, and KMAs into annotation-free anatomical masks at scale. ANA-US then combines two self-supervised objectives on unlabeled butterfly and camas data: multi-scale, BYOL-style anatomy contrast that pulls together the same structure across views while repelling different structures, and a contextual prediction loss that reconstructs corrupted core regions using ultrasound-specific perturbations, such as pixel shuffling, Gaussian speckle noise, and occlusion, across 6 public benchmarks, including POCUS, BUSI, UDAP-B, TN3K, and HMC-QU. ANA-US reaches 96.2% accuracy on POCUS, 87.1% on BUSI, and 85.9% DICE on UDAP-B, outperforming the strongest ultrasound-specific baseline IVPP++ by 3 points, 3.6 points, and 2.3 points respectively. Ablations show that removing LP-SAM drops UDAP-B DICE by 15.7 points, making anatomy-aware mask generation the dominant factor behind the gain. The retained ResNet 1.8 encoder remains real-time, processing a 224 x 224 image in about 0.45 milliseconds on an RTX 4090. Let's explore the second paper: Contrast to Detect Dynamic Graph Contrastive Regularization for Unsupervised Anomaly Detection in Multivariate Time Series. Contrast-AD is an unsupervised multivariate time series anomaly detector that targets 2 failure modes in prior work. Reconstruction models often reproduce anomalies too faithfully, and graph contrastive methods usually assume static relational structure. The novelty is a dynamic graph contrastive regularizer that treats structural drift as a signal. The architecture combines a multi-perspective embedder that jointly encodes temporal, attribute-wise, and structural views, a frequency-aware attention mixer that applies FFT-based top-K spectral filtering before attention to suppress noise leakage, and a dynamic graph contrastive learner that builds sparse snapshot graphs from batch-level dynamic time-warping distances and contrasts the most divergent pair against a stable anchor. On 5 benchmarks, SWAT, SMD, MSL, PSM, and SMAP Contrast AD achieves the best mean F1 on all 5 and the best AUC on 3, with statistically significant gains on SWAT and PSM. For example, it reaches 88.24 F1 and 93.6 AUC on SWAT, 78.87 F1 and 98.66 AUC on SMD, and 91.17 F1 and 97.79 AUC on PSM. Ablations show the graph contrastive term is essential. Setting its weight to 0 drops SWAT F1 from 88.24 to 73.84 and SMD F1 from 78.87 to 50.01, while negative contrastive weights consistently outperform positive ones, confirming that soft regularization is better than strict invariance under non-stationary dynamics. Let's explore the third paper: The Implicit Bias of Depth from Neural Collapse to Softmax Codes. The paper studies the deep unconstrained feature model under multi-class cross-entropy without explicit regularization, isolating the implicit bias of gradient flow in deep linear classifiers. Its main result is that depth itself induces a low-rank bias that competes with neural collapse. For L equals 2 and K is greater than or equal to 6, or L is greater than or equal to 3, and K is greater than or equal to 4, the asymptotic max margin landscape is no longer benign, and deep neural collapse is not globally optimal, even though it remains a local optimum. The global optimum in the large depth limit is a rank 2 softmax code, where class means lie uniformly on a circle, matching the D equals 2 bottleneck solution of Jiang et al. 2023. The mechanism is spectral. Low-rank matrices propagate norm more efficiently through repeated products, so they achieve larger logits and smaller loss than the simplex ETF geometry associated with neural collapse. Dynamically, under Hadamard initialization, the singular value flow reduces to explicit ODEs, showing a rich get richer effect, where larger singular modes grow faster near the origin, making neural collapse unstable for L is greater than 1 inch the linearized regime. This instability grows with depth, while random Gaussian initialization at large width counteracts it by biasing early motion toward neural collapse through concentration of measure. The paper proves dz dt at time 0 converges in probability to L plus 1, 2L, sun, and t. Experiments on deep UFMs and ResNet. 2 zero heads trained on MNIST and CFAR. 1 0 confirmed that increasing depth lowers effective rank, increasing width raises it, and lower rank solutions tend to generalize worse. That's a wrap on today's AI paper highlights. Thanks for watching.